Hello everyone, my name is Luke Wagner. To introduce myself, I thought I would give like a short story of my path to here that might be like relevant to this workshop. So I started at Mozilla 10 years ago on the JavaScript engine during the midst of the kind of JavaScript performance wars. And a year or two after, they started the Mozilla Games program, which was led by Martin, who I see is here. And so the goal at the time was if we make the web platform better for games, then we'll, in addition to be allowing games to run, which are really cool, be making it better for all sorts of use cases. And that matches what I heard earlier Francois saying. So that was the goal. And so I was put on this team as the JavaScript liaison to fix the JavaScript problems that we saw. And at the time, Mscripton was this emerging tool to compile JavaScript or C++ to JavaScript, and it was producing, JavaScript files that were just 10 to 100 times bigger than we'd ever dealt with before, which created challenges. And after bashing my head against the problem of how do we make this stuff run well, like native, smooth startup, or not drop frames and all these things, ASM.js came out of this as a research experiment of if we keep JavaScript the same, but put all the burden on the producer to give us the maximally optimizable JavaScript, what's the best we can do? And the surprising answer was we can do really pretty well. And so we got these big game engines and these pretty amazing demos running, and then it was running well enough that people actually started using this in production in like Facebook games and all sorts of other places. We had Epic and Unity and all these big game engines targeting this. And so this created a context where we had eliminated all the kind of accidental problems and said, what are the theoretical limitations with ASM.js and kind of confining ourselves to JavaScript. And at the other side, we had all these concrete use cases of, showing people really wanted this stuff. They really wanted this to work. So this gave us the context to propose WebAssembly, which we did, with all the engineers from all the other browsers leading us here today. So yeah, this was an example of just focusing on the question of how do we, if we make games run well on the web, what other cool things will pop out of this? So, right. First going to start with kind of just a status update of where we now. So in 2017, we shipped the MVP, which is kind of the initial version of WebAssembly in 4 browsers. That was about 2 years after the very first beginning of creating the WebAssembly CG. So about 2 years to do that. And basically immediately, at the same time as it was moving to shipping, we were thinking about what's the next wave of features. What are the next things we want to add? And the process for this is a little like, if you're familiar with TC39, how there are a set of features and they have stages. And from the first stages of we're even looking at this problem, we want to make proposals, to stage 4 being, we pretty much have a finished design here and we've tested it in browsers and now it's preparing to ship. So back, linking this all together, we worked on this roadmap, which my colleague Lynn Clark wrote up in this great thing, which you can see that we had a whole bunch of things we wanted to fix after, and I won't go into all the details here, but you have use cases of, on the one hand, increasing WASM's use from JS with kind of helping small modules and using WebAssembly integrated with JavaScript, to supporting heavyweight applications, supporting languages that want to compile to JS that use GC, supporting frameworks, and then all sorts of exciting stuff happening outside the browser. So we have this kind of overall roadmap. I encourage you to check out this blog post to find a lot more details about it. And, whoops. And based on this, we have currently a set of proposals that we're working on. So to give kind of a very short summary, some very small additions, just new operators that are kind of like just new things that weren't in the MVP that you might want to do, being able to convert float stints without trapping when you overflow. Some interesting things like reference types that I'll talk about later today, being able to do bulk copy of large amounts of data, binding closer to JavaScript with int64, integrating with the ES module system. There's a proposal we've been working on for a long time, initially called SIMD.js, but now reframed in terms of WASM, fixed with SIMD. And then a bunch of other features that are kind of earlier and moving along, including WebIDL Bindings, which I'll be talking about today. So I'm happy to talk about any of these features. I would recommend, if you're interested in what's going on, to check out this proposal. It's maintained by a community group member that kind of summarizes all what's happening in the community group. So that's at this proposals repo. So, right. So next, I'm going to spend most of my time talking about what I thought might be relevant to the people in the workshop, which is we have all these web APIs that are used from JavaScript. How do we efficiently access those from WebAssembly? So this has gone by different names, so I'm just going to put a star, but it's always had the name bindings in it. So to give a little bit of history, in 2017, we shipped this MVP. And in this MVP, there's only 4 value types. So everything in your whole world has to boil down to one of 2 sized integers or one of 2 sized floats. So the question is, how can WebAssembly call web APIs? They use a lot more than just these 4 data types. If we want to make WebAssembly APIs, or if we want to make web APIs that are good for WebAssembly, do we have to only use integers in the signature? That seems like a regression in multiple ways, especially since these same web APIs are exposed to JavaScript. So in that same year, take one was what we called host bindings. And if you've looked at this, you might have seen something called host bindings. And I have links to the original kind of presentations that we gave, kicking that off. And so the observation at the time was, well, WebAssembly does have this thing called a table. Tables can hold opaque things that can be pointers. In general, we can't give WebAssembly transparent pointers because the bits of this pointer, it's a security implementation detail that it leaks information about what's going on in the process. We can't take these pointers and store them into the linear memory because it's a big array of bytes that can be arbitrarily mutated and observed by WebAssembly code. So instead, we can put them in these tables, which are like typed arrays that hold these opaque values. So since we're putting all these things in tables, let's make it able to, when we're calling web APIs, to efficiently put things in and out of these tables. So you have an I32, which is an index in the table. And when you call the web API, it could automatically use that I32 to pull out the actual value from a table and pass it to the web API. And on the way back, it would go into the table, and you would get the index back in WebAssembly. So it was completely based on all the interesting values go in tables. And this became increasingly awkward as we started to really consider it seriously. Like, some people apparently had already really thought about this in the GNOME project, and so they started asking us, like, well, what about this? What about this? What about this? And we're like, oh, we'd add this, we'd add this, we'd add this. And after a while, we're like, this is not natural. So also, we were solving the problem of how do we do it at all without using JavaScript glue, but we weren't actually making anything faster. In fact, as we started to think about it, this might actually be slower than just using the JavaScript as glue. So that was also awkward. So what came out of this was realizing we needed a new fundamental concept in the core of WebAssembly, and that's reference types. And reference types are values that you cannot store into the big array of bits. So they can't be scrambled. They're an actual real value. And that means they can point to a DOM object. They can point to a JavaScript object or anything. And so a whole set of types and operations for dealing with reference types. In particular, the reference types form a hierarchy where any ref is basically equivalent to a JavaScript value. And this is what's implemented in at least Firefox and Chrome today. It's not yet shipping, but it's behind various feature flags, and it's moving towards actual release later this year. So with any ref, you can have a core WebAssembly value that is any JavaScript value. Anything you can do in JS, you can stick in WebAssembly. You can't store it into the big linear array of bytes, but you can do a lot of other cool things with it. And then after we start with that any ref, which has no static type info, right? It's anything. Therefore, if you try to pass it to a web API, you're going to have to necessarily do a dynamic type check on the way out. We've been talking about more specific reference types that have more actual static type information. But this is, and these we're considering incrementally. So you have a type of, say, functions, a type of structured data that has a fixed set of properties, a fixed set of types of those fields, arrays with fixed set of element types, and all these things. So that's work on reference types, which is going on in the core WASM spec. And yeah, it gives WASM first-class host values as a consequence. So building on this, there's kind of a take two, and we're calling this one WebIDL Bindings. And so it focuses on the problem of, I'm going to make this go away. Let's focus on efficiently binding to WebIDL. So it's a kind of a refinement of the previous project scope, and we'll be building on reference types, because these are now in the core. And efficiently here means we don't just want to bind them at all. We want to eliminate some of the copies and the garbage and the auxiliary calls that would have had to have been made and aren't being made today if you're using WASM. So we actually want to be faster than we can today. And we want to focus, if we want to be fast, we have to focus on what we're binding to. So binding to any arbitrary host thing, that's a pretty open-ended problem. You can imagine spending a decade trying to define a meta-ontology of all the host possible things. But if we just focus on WebIDL, that's a lot more concrete. And we can do that. So, so that's the rescoped proposal that we're working on. So just to give a little more details about that, in the MVP, let's say you have a WASM module. And WASM modules exclusively talk to the outside world through their imports and exports. So if you want to call other WASM, well, then we have a very efficient way that this works. You know, your import imports an export of some other WASM module. In the implementation, the one WASM module has one piece of code, the other WASM module has another piece of code, and linking them together is just like patching a pointer. So it's indirect function call, very fast hop from one WASM module to another. In comparison, when you try to call a web API, this is what necessarily happens today. So first, we're going to go through semantically the WASM JS API spec in which the WASM values are converted to JS values. And now these JS values will be things like numbers, because that's what we started with. And so there's going to be some glue code that runs on those values to massage them into what WebIDL wants. If it wants a string, then we're going to be reading bytes out of memory to create the strings. If we want to make a dictionary, we're going to have to be creating a JavaScript object that has the right properties. So some glue code will run, and then we're going to call the web API, and this will necessarily go through the WebIDL specs ECMAScript binding, which takes those JS values, massages them to get core abstract WebIDL values. And that's what we define all of our web API specs in terms of, these abstract WebIDL values. So each of those hops isn't just in the spec. There's pieces of machine code that have to be generated to do each of those hops. So there's that trampoline to get out of WASM into JS. Then we do some machine code which runs the JS. And there's a trampoline to hop out of JS into the WebIDL bindings. Then there's some C++ that's generated from the WebIDL that massages them into the core Gecko types. And finally, we got to the actual C++ that was actually written by a Gecko programmer. So cost and also kind of complexity. So with the proposal, what we want to do with WebIDL bindings is make it look like, well, I'm going to build up to it. So first, the way we're thinking about this is you take the WASM module, and then it's wrapped with something we're calling WebIDL bindings. And when we say wrapped, this means that we can implement this whole feature as a polyfill. We can create JavaScript that literally wraps the WASM module and massages its inputs and outputs to produce what we want on the other side. So that's good. Polyfills mean we can iterate early without having to implement anything in browsers. And then what this layer does is we'll take the WASM values and we can directly produce the WebIDL values. As in the spec will say how to go from WASM values to WebIDL values, which goes directly to the web API. And the interesting thing, which is kind of the cool thing, is those arrows that go in and out, they're not just fixed, where here's the types, this is exactly what happens. They're programmable. You can actually write little declarative expressions in both directions that say how you want to take the WASM values and produce the target values, because there's not just one way to represent a DOM string. If you're using a linear memory, there could be several different codings. Is it null terminated? Does it have a length? If you're using GC types, completely different options. So we need these to be programmable and extensible over time. So there's one direction, which is incoming, when you start with a WebIDL value, like a DOM string, and put it into WASM. And there's outgoing, which takes WASM values and produces the WebIDL values. So both of those are programmable with a set of operators that are tailored to this task. So that's kind of the structure of the existing proposal. It has an explainer, and I'll talk more about what's the status of that later. So just to give an idea, so in this last one, we have these WebIDL values. So the question is, well, they're values. They must have types. What are the types? So here's a sketch. So we start with WASM as a thing called reference types. That's that thing that's being defined and nearing shipping that's already in WASM. So we're going to import all those. We want them. And also, WASM's integers don't have sign. They just say, I've got 32 bits. You shall interpret them as you wish. So we need to know the sign, because if it's flowing out to the outside world, we need to know whether this is a signed or unsigned value. So we break it down. And with those, we can now build up what's actually the binding type. So you start with your WASM references, and this is what we can use to express in WebIDL any interfaces, promises, lots of things. Take the number types, and those correspond to the WebIDL byte, octet shorts, and all those things. We would have an abstract stream type that was co-expressive with DOM string. When you want to pass an array buffer, there would be some bytes type. For lists, or for typed array views, there would be a view type. Similarly for lists, records, dictionaries is kind of a misnomer. And everywhere else in the world, dictionary means like a hash map sort of thing. In WebIDL, it actually means a record, so we call it a record. Stop confusing everyone. And then similarly, variants and a function type for callback. So the idea is these types that would be defined in the WASM binding spec would kind of correspond in a direct way to what WebIDL wants on the other side. And then to view how you produce these things, in the simplest case, there's nothing to do. WASM has a reference type. It says I'm pointing to some DOM node. And if I want to pass it to WebIDL, I just say, as says, just do the trivial thing. So it's not very interesting. This one, if this was the only problem to solve, we wouldn't need any interesting proposal. More interesting one is string. So one way is WASM would pass two I32s, and these would describe a string that sat in linear memory. The first one would say, what's the offset? And the second one would say, what's the length of how many bytes do I read? And then the operator says, produce a string, assuming the UTF-8 encoding that's coming from linear memory, and I would get a string. And that would be for the producing side, so that's an outgoing expression. And then on the other side, we'd have an expression that says how I want to consume a string. And I need to say, here's a function that you can use to allocate bytes in the WASM memory. And here's a function called free when it's done. And after the host has called the allocator, written in the bytes, it will return the offset and the length. So yes, the next side, or the next one, there's a different way to produce a string, which would be to, when we have fancier reference types, you can pass a reference to a GC allocated array of bytes. And there it's kind of the same. We're saying they're UTF-8, but they're allocated in GC memory. And we can ask for it on the other side as in GC memory. And then lastly, we can have opaque types that say, I don't know what this is really referring to, but it's coming from the host. And if it happens to be the DOM string type, we can just pass it through. We already have a string. We don't have to build one. We got one from, say, a previous web API call. And the interesting thing is all of these are composable. So on the one side, you can pass strings with one set of representation, and you can receive them with another one. And this gives a lot of flexibility. And a different example would be a record. And this shows how these types have to be compound, because a record itself contains strings. So one way is I can have a record that's sitting in linear memory, or sorry, sitting in GC memory with the right reference type. Or I can build it from two strings, and those two strings can be built up from linear memory. So it's a compound sort of situation where you're building up the small things and then building up into the bigger things. Yeah. So a general goal is we want direct access from WASM to web APIs defined in WebIDL. And we want it to be direct. And so what does direct mean? There's two ways that you can be direct. One is how WASM imports functionality, and one is how WASM then calls the functionality afterwards. And in particular, we're trying to replace glue code. So what's the glue code we want to replace on the importing side? So when we instantiate a WASM module, we have to call this function today. And it gives the WASM module, which is just the code, and then we give it what it has access to. And by default, WASM doesn't have access to anything. You have to give it whatever WASM can call in the import object. And the import object is just something you make in JS. So if you want WASM to be able to call create elements, you would have to put that into an import object that you then pass into the WASM. So if we want to optimize, if we want to have direct access to web APIs, that's the glue code we'd want to somehow replace. Calling is very different. Let's say I want to call create elements, and I want to pass my WASM types, anyref, my two ints. Well, today, you would have to wrap it in a JavaScript function that takes these three things as these arguments, and then it gets an array buffer from memory. It creates a view. It uses the text decoder to decode from the bytes into an actual string, and that we can pass to the real create element function and return the result. So this is glue that you would want to remove on each individual call to a web API. So removing this type of glue code, this is what the WebIDL Bindings proposal is trying to remove, is you don't have to write this. You would do it in this bindings layer that wraps the WASM module, and also do it faster than actually doing all those steps individually. And this glue code is actually addressed by a completely separate set of proposals that are being worked on and relevant to the W3C. One of them is called WebAssembly ESM integration. This is being able to treat a WASM module as an ES module. So the WASM module is loaded by the HTML loader spec. You can import all the things that are exposed to the HTML loader. Once you have that, then there's an independent work on having built-in modules. So at the moment, every module in every ES module that's loaded on the web, if it imports something, it has to come from a different piece of JavaScript, all the way until it just has to terminate with your loading ES modules. So built-in modules is like saying the browser itself can implement modules that can be imported by JavaScript. And import maps is the way of saying I'd like to virtualize or disable or hide or mess with what's available by default. And then lastly, Git originals is saying let's take all the existing web APIs and expose them as built-in modules, providing the original value. So if you put all these things together, you can have all web APIs exposed as built-in modules, which are importable by WASM. So we load the WASM module just with an import statement, and it can import all the web APIs directly without needing any JavaScript glue. So this is what we're not solving in the WASM CG. It's being solved by the rest of the web platform. So that's the proposal. So we've done some prototyping work since kind of agreeing on this direction at TPAC 6 months ago. Jacob Gravel at Google has done some experimentation making a polyfill that's kind of oriented towards C++. The Rust folks have been working on this WASM bindgen project you might have heard about that it lets you write, if you want to import, say, console.log, you would make a Rust function called log, and it takes just a Rust string type. And you would say where it comes from on the JS side, and it will generate all the glue code that is necessary to make that just work. So calling and making a WASM module that calls log, console.log, is as easy as declaring that function, and then you can call it like a normal Rust function. So the goal is to basically make that work except without the JS glue code, using these new features as they become available, and providing a fallback to JavaScript glue when they're not yet implemented in browsers. And lastly, at Google, another engineer has worked on a cool performance benchmark to show that we can actually, to validate the assumption that we can get speedups. So we took a workload where, let's call it, which is kind of a worst case thing where we're calling through the bindings over and over, doing some WebGL things, and these are some very hot functions where we don't do a lot of work actually in the functions, so you spend a lot of your time hopping in and out, and found that by simulating what WebIDL Bindings should be able to do, is able to get significant speedups for doing these calls. And this very all preliminary experiments, not done by implementing the feature, but by saying the feature should be able to do machine code like this, so I'm just going to write it by hand. But still good to have validation early and often. Right. So that was I just added this slide because somebody mentioned earlier interest in WASM debugging. So this was discussed at the WebAssembly community group meeting last week. I have a link to the minutes to hear more of the discussion. But what's emerging is everyone really cares about this. And we've cared about it actually for a long time, but it's been paralyzing to say what's the right way to solve this? Where do we solve this problem? And ideally, we don't want to have to build in dwarf debugging into the browser, each browser. That's problematic in a number of ways. So the idea is to have expose a set of interfaces, not to the web content at large, but maybe to extensions. And the interfaces would describe, one, the interaction between a language-specific debugger and the browser dev tools. And the other interface would be how a language-specific debugger inspects the runtime state in WebAssembly. So this is where you could put the dwarf logic, and it could be itself sandboxed in WASM, so that way if there's a bug in the dwarf logic, it can't exploit the browser. And it could be shared between browsers. So all that's to say is, there's a good chance we're working on a story to be able to have like first-class dwarf debugging if you're a C++ or Rust user, or other debugging things for completely different languages that don't have dwarf, as in some ways that's shareable between browsers. So if you're interested, we already, maybe a year ago, created this debugging subgroup of the WebAssembly CG, specifically to focus on this thing. But then we were, again, paralyzed by what do we actually do? And so there hasn't been much activity. But after the last discussion and interest from a number of groups, I expect activity will resume in this debugging subgroup. I have a link to it has a repo on GitHub under the WebAssembly org that you can check out. And so if you're interested, I'd watch that and potentially join in.